In this video, we are going to talk about graphing cube root functions, and shown here in yellow is the parent function of the cube root. On the left, we use the radical symbol. You could see that this is the principal cube root of x, and on the right, it's written as a fractional exponent. These two functions are equivalent. Now, the function written in blue, y equals x cubed, is not the same as the two written in yellow. If the exponent is 3 as opposed to 1/3, we refer to that as a cubic function. And we will not be covering the cubic function in this video. We are going to focus on the cube root function. Folks, throughout the video, I'm going to be writing the radical symbol, and I want to apologize ahead of time. If I forget to put a 3 here, please understand that that 3 does belong here. I will not be dealing with the principal square root, which, as you know, is the radical sign with nothing placed here. That would be an understood principal square root versus the 3. So again, my apologies if I forget to put the 3 in. One quick note about drawing this radical symbol. I think it's a lot easier if you draw the radical symbol first and then place the appropriate root, whether it's 3 in this case, or 4, or 5, etc. I find that if you put the small number first and then try to build the radical sign around it, you get this wide V here, and I don't think this is as aesthetically pleasing as the one above. Another note about drawing radicals is be careful about that root sign. In other words, the 3 belongs here. If you're not careful and you put the 3 here or in proximity here, you might confuse these two radicals. In other words, if you intend to write the cube root of 3, make sure you put it far enough to the right so it doesn't get confused with a factor out front. This would be 3 times the square root of something versus the cube root of something. Folks, these are the type of functions we're going to be looking at in this video, and we're going to utilize this transformation equation. Notice how I have the hidden one highlighted, because you cannot really analyze the transformations unless and until you have a positive 1 in front of that parentheses. We're first going to look at the parent function, the cube root of x, and then I'm going to tell you what to do when the signs on the outside of the radical are the same like they are in the first two functions, and when they're different like they are here. Folks, here's a classic example where I forgot to write the cube root. Again, if I do that throughout this video, please understand there really should be a 3 here. After I review the parent function and the effect of sign changes, we're going to look at transformations, and that's where we're going to utilize the formula in red. First, I'm going to tell you what to do when there's a constant under the radical, when there's a constant outside the radical, and when you have both. Finally, we're going to introduce coefficients outside of the radical in addition to transformations. And the last few functions we're going to look at are when you do not have a hidden 1 in front of that x, but rather have a coefficient that is not equal to 1. And as I'll show you, we will have to do some manipulation in order to get this blue function here to look like this red transformation equation where there is a hidden 1 as shown. In a previous video that I made on parabolas, I mentioned that when you analyze parabolas, you only need to look at 3 of its characteristics in order to sketch a relatively accurate graph. And those 3 things are, number 1, where is the vertex? So here, the vertex, any vertex, is going to have a coordinate point, an x and a y, and here the vertex would be at the point x equals 5, y equals 2. So identifying the location of the vertex is the first thing. The second thing is whether or not the parabola is facing up or down. So if this a value here in the front of the vertex equation is positive, you'll see an upright parabola like the red and the white one shown here. However, if the a value is negative, that parabola is flipped upside down. The third thing is whether or not the parabola is wide, like the blue one, narrow, like wide like the white one, narrow like the blue one, or what I like to call perfect, which this red one is. The parabola's width is quote-unquote perfect when this a value is positive or negative 1. When it's greater than 1, when the absolute value of a is greater than 1, you will see a narrowing of the parabola, again, whether it's positive or negative. And finally, if that a value is a fraction, you'll see a widening of the parabola. Similarly, when we evaluate cube root functions, we only need to look at 3 characteristics in order to provide a fairly accurate sketch of the graph. The first is, where is the inflection point? See this point right here? This is the parent graph, y equals the cube root of x. So in this particular blue function, both the h value and the k value will be 0. So here in blue, they're hidden zeros. They're there, but you don't see them. Here, our inflection point would be hk. The inflection point is where the trajectory of the graph changes. It's similar to the vertex of a parabola. As you know, if you have an upright parabola, it would look something like this. Then it hits the vertex and it changes trajectory. Same here with this inflection point. So the first thing is, where is this inflection point located? And this equation will tell you that. The second thing is whether or not the first move as you move from the inflection point left to right is up, as is shown here, or whether it's down. It will be flipped. It will be down if this a value out front was negative. Here there's a hidden positive 1, so the first move is up. And the third issue is how long this vertical line is. You could see the cube root function, there's a vertical line that goes through the inflection point before you start to see curving of the graph. Depending on the a value, the length of that particular vertical segment would change. For example, if I put a 3 here, the length of this vertical segment would increase. So you would have a graph that looks like this, with a elongated vertical segment. Similarly, if one were to put an a value that was a fraction in front of the equation, so rather than a 3, if we change that, say, to a 1/2, like so, the length of this vertical segment would shorten. So using these 3 characteristics, where is the location of the inflection point, whether that first move is up or down, and how long that vertical segment, gleaning that information from this equation will allow you to get the intuition on the graph and provide a fairly accurate sketch. Let's now look at the graph of the cube root function and the effect of negative signs, both inside the radical and in front of the radical. So shown here is the parent function, y equals the cube root of x, with no negative signs. So you could see, again, the inflection point is at 0, 0. The first move, as you move from left to the right, is up. There's no flip. And there's a vertical segment here, which is what I would call perfect because there's a +1 in front of the radical. So let's see what happens, folks, as we introduce negative signs. Now, the Desmos requires that you write this function as a fractional exponent, but instead of that fractional exponent, you can just envision a radical sign with a 3 in the cube root position. So here we see the parent function in red, and there's a plus sign and a plus sign, and you would just see this as y equals the cube root of x, and the plus signs would be hidden. But look what happens when we introduce a negative sign inside the radical, and now the signs are different. So the plus sign is outside of the radical, the negative sign is inside the radical, and when I press this button, you'll see the blue graph. So you see this has been flipped. As we move from the inflection point from left to right, the first move is down. Okay, let's see what happens now if we look at this next function. Here, the negative sign is outside the radical, the positive sign is inside the radical. The signs are still different. Let's see what happens. it becomes green because now the green and the blue are superimposed. In other words, it's the same graph. So whether you have plus minus or minus plus, you will see a flip of the graph. Finally, if you look at two minuses, again, the signs are the same. When I click on this radio button, it's going to be superimposed with the original function. That is because the signs are same, you will get a normal function. Signs are different, you will get a flip of the function. Shown here is a review of what we just did on Desmos. And I think, folks, this would be a nice screenshot to take to keep to summarize this information. So here in blue, we have blue functions where the signs are the same. Positive, positive, negative, negative, and we see a normal blue function where the first move off the inflection point as you move left to right is up. And here in white, these two white functions, the signs are different. Plus minus, minus plus. You will see a flip of the function where the first move from the inflection point is downward as you move left to right. Okay, let's now sketch some cube root functions. And by sketch, what we're going to do is we're going to use our intuition using this generic equation and our function to sketch the graph. Notice, when I did the generic equation up here, I put the positive 1 in front of that x. We cannot use intuition on this function unless and until there's a positive 1 there. Starting with this function on your left, we do indeed have a positive 1. First thing we're going to do is we're going to get our inflection point. Recall, it's going to have a HK coordinate. If we go to our generic equation, we see there's a negative in front of that h. That means we take the opposite. So we put a circle around what we see in the real world equation, and as we bring it into our answer, we flip the sign. For the negative 3, because there's a plus k out here, we leave that as is. So our inflection point is going to have the coordinates negative 2, negative 3. Next thing we do in our analysis is we look at the a value. If the a value is positive, that means we are going to open up going left to right as normal. If it's negative, it's going to be flipped. We do not see a negative here, nor do we see a negative inside the radical. That also would flip the graph. So positive, positive, signs are the same. We know that this graph is going to open up and to the right like so. The a value, the absolute value of a is 1. Therefore, the vertical distance through that inflection point is going to be what I like to call normal or perfect, which looks like so. Our graph, as mentioned, is then going to open up as you move left to right, and then this other side is opposite. So there is your sketch. The next problem shows a negative sign out front. Before we do any intuition, we double check that this coefficient with the x within the radical is positive 1, and indeed it is, so we may proceed to using intuition. The h coordinate of the inflection point is going to be flipped. The y coordinate is going to stay as is. That's going to put it as plus 2 minus 1. There is our inflection point. Now, the vertical distance here through the inflection point is going to be normal because the absolute value of this coefficient out front is 1. However, because of that negative sign, because this is a negative and that's a positive, they are different. Our first move is not going to be up, which is normal, but rather it's going to be down like so. And we're going to go opposite up above. So this graph has been flipped from normal. Normal would be dotted, but because of that negative sign, the solid is what this sketch would be. Okay, let's move to the next one. Can we use intuition here? Yes, because this coefficient, is positive 1. Doesn't matter what's out here. Don't forget, the previous example had a negative out front. That's okay. We're talking about the coefficient within the radical associated with x. So let's do the intuition on this graph. Our inflection point is going to be -3, +1. -3, +1. This graph is going to open up and to the right. However, the vertical length through that inflection point is going to be longer because of the 2. So let's go ahead and make that a little bit longer than normal. And we're going to open up to the right and down to the left, like so. In our next function, we can clearly see we are not ready to sketch this. We cannot use our intuition to evaluate this function because this coefficient is a -1 as opposed to the required or mandated +1. We can briefly just notice that the signs are the same, so we know there's going to be no flip in this graph. But as mentioned, we cannot do things like evaluate the inflection points and or have any idea what the coefficient out front is going to be and determine the length of the vertical segment as of yet. So let's take a look at this function again. Sorry about that. And let's make this a positive x. So how do we do that? Well, we would pull out a -1 out front. Okay, we're still under the radical sign. And then this would become x, and this would be -3. Okay, so our new function is going to be the cube root of what we see here with a negative out front. Because these are a product, both under the cube root sign, we can give them their separate cube root signs. Let's not forget our +1 at the very end. That's going to be our k value. This is the original -1 that was hidden. Here's the cube root of -1. That's pulling that factor out and giving it its own cube root sign. So this is going to end up being -1 times -1 times the cube root of x minus 3 plus 1. This is going to become +1. So our new simplified function is going to be the cube root of x minus 3 plus 1. Folks, we now can use that yellow simplified version on the upper right as our function to apply intuition. First thing we want to do is find the inflection point. We know we have to reverse the sign on the x coordinate, so we're going to have +3, and we're going to keep this k coordinate, k, which is the y coordinate of the inflection point, as is. Flip this one, keep this one the same. Recall that's because of that negative sign that we flip it, and that positive sign means we keep it the same. So here's our inflection point right here. Our a value didn't change. The absolute value of it is still 1. So the length of our vertical segment is going to be the same. And since we have no negatives at all in the simplified version of the function, and we had the same sides originally, we know that this function is going to behave normally without any flip. As we examine our next cube root function, we immediately notice that we have an 8 with the x instead of a +1. So we are not ready to use intuition to sketch this graph until that becomes a 1. So what we're going to do is we're going to factor out an 8 first. And we know that's going to be x. And this is going to be a question mark. We don't know what goes there. So we do a little miniature equation. We know that when we distribute the 8, we have to get 2. So this becomes 8 times question mark equals 2. We divide both sides by 8, and we get question mark has to equal 1/4. Okay, so we're going to rewrite this radical as y equals the cube root of 8 times x plus 1/4 plus 2. Now we're going to give each of these factors its separate radical. So we are going to have the cube root of 8 times the cube root of x plus 1/4 plus 2. This, folks, the cube root of 8 is 2. So our final simplified function is going to be, that should be a y. Y equals 2 times the cube root of x plus 1 over 4 plus 2. We are now ready to intuitively sketch this graph as we have positive 1 with the x. So let's go ahead and do that. Just do a little bit of cleaning up here. I apologize for the delay. Okay, what is our inflection point? We pull this out and we flip the signs. That's going to be negative 1 over 4, and this stays as is. So negative 1/4 positive 2 is going to be something in this vicinity. We notice that our a value is a positive 2. That means the fact it's positive means when it emerges from the vertical segment, it's going to go up and to the right. And our vertical segment is going to be slightly longer because there's a 2 there instead of a 1. So our graph is going to look something like this. For the remainder of the video, we're going to switch gears and talk about how to graph a function. Graphing a function is more precise than what we've been doing up until now. Up until now, we've only been sketching the graphs. Recall when we have sketched our graphs, we've utilized this transformation equation. If necessary, we manipulated the equation algebraically in order to obtain a positive 1 coefficient with this x. At that point, we extracted the inflection point, h comma k. Recall we had to flip what we saw based on the negative in the generic equation for the x-coordinate of the inflection point, and we kept the y-coordinate as is because of that positive in the generic equation. Next, we used intuition. We decided, are we going to flip the graph based on the combination of negative signs here, specifically whether they were the same, in which case there would be no flip, or whether they were different, either plus minus or minus plus, in which case we would flip the graph. And finally, we would use the absolute value of this a coefficient out in front of the radical to determine the length of that vertical segment, the midpoint of which is the inflection point. Now, folks, when we talk about graphing, we're going to do things a little bit differently. And we're still going to utilize the transformation equation. We are still going to manipulate the equation if necessary in order to get a positive 1. But now we're going to focus on what's underneath the radical. Now let me show you what I mean by that. Okay, so when you graph a function, you want to try to determine perfect cubes. What do I mean by that? Well, if you're in class and a teacher poses this question, what is the cube root of 32? The way I like to teach this is to look for perfect cubes in the radical. So what are the perfect cubes? We have 1 cubed equals 1, negative 1 cubed equals negative 1, 2 cubed equals 8, negative 2 cubed equals negative 8, 3 cubed equals 27, and negative 3 cubed equals negative 27. Now it turns out when we're graphing, the 27 is just too big to work with. So we're going to focus on 1s, negatives 1s, 8s, and negative 8s as we graph. Let me show you what I mean. Folks, if you were going to try to determine the algebraic simplification of the cube root of 32, what I would recommend is that you look for a perfect cube within the 32. So in this case, there is a perfect cube because 32 can be written as 8 times 4. When you break this 32 into a perfect cube and another number, you give each of them their own radical. Now we have a perfect cube out here which can be simplified to 2. So your final answer becomes 2 times the cube root of 4. We're going to use this concept to look for perfect cubes in this radical as we plot our graphs. Here is a graphic representation of the parent function y equals the cube root of x. You could see it right here. Now here's our graph. The hk coordinate of the inflection point is 0, 0, and that's because there's no transformations. It's just y equals the cube root of x. Notice this vertical segment is what I would call perfect. That is because the coordinate out in front of the function is 1. The absolute value of 1 is 1, so this is going to have a perfect length. The inflection point is going to be at the midpoint, and it's going to open up as you move from left to right because there's no flip, no negative signs. Look at these points here, folks. We have 1, 1. 1's a perfect cube. Here, we have 8, 2. 8 is a perfect cube. Going in the opposite direction, -1, -8, perfect cubes. We are going to utilize that to help us graph. When we graph, we're going to do what's called plotting points. Once we get our equation simplified, once we get a +1 in front of that x and we extract the the inflection point, we will then plot points. And I'm going to show you how to do that in our next segment. Let's start with our first function, and we're going to graph this more precisely than a sketch. First thing, folks, is to manipulate this equation so you have a +1 here. We don't need to do that. Next thing, we are going to extract the inflection point by circling this, flipping it, so the x-coordinate or the h-coordinate is going to be -3, and the k-coordinate or the y-coordinate of the inflection point is going to be +1. So let's go ahead and plot that. We have -3, +1. So that's our inflection point. We know that our vertical distance is going to be longer, and we know that the graph is going to open up as you move from left to right. But unlike when we sketched it, we are not going to draw that in. That's our intuition, though, based on having the inflection point and looking at the other values in the parent equation. Folks, the next thing we're going to do is we're going to move 1 unit to the right and 1 unit to the left and use these x values. Okay, so this x value and that x value, and we're going to plug those into the equation to get our y value. So first we're going to use, instead of x equals -3, we're going to do x equals -2. And then we're going to do, instead of x equals -3, x equals -4. So what we're going to do is do f of -2 to get our y value and f of -4 to get our y value. F of -2 is going to be y equals 3 times the cube root of 1 plus 1. This is going to be 1. 3 times 1 is 3 plus 1 equals 4. So our first point is going to be -2, 4. Let's go ahead and plot that now. I should say our first point in addition to the inflection point is going to be right there. Okay, that's -2, 4. Next, we're going to do f of -4. If we do f of -4, we're going to have y equals 3 times the cube root of -4 plus 3 plus 1. That's going to give us the cube root of -1, which is -1, times 3 is -3 plus 1 is going to be -2. So there's our next point. Now, some would argue that that's enough to do a graph, that you could connect those 3 points and use your intuition to remember that the graph is going to just continue out this way. It's going to have a vertical segment, encompass these 2 points, and continue. But to be more accurate, we're going to get 2 more points. Folks, what we're going to do is we're going to set x plus 3 to perfect cubes, and they are 8 and -8. We are then going to solve for x. So here we're going to have x equals +5, and here we're going to have x equals -11. Then we're going to do f of 5 and f of -11 to get the y coordinate of those points. So let's do that. Okay. F of 5 is going to be y equals 3 times the cube root of 5 plus 3, which is 8, plus 1. Y equals 3. The cube root of 8 is 2, plus 1 equals 7. Okay. Next, we're going to next we are going to evaluate f of negative 11. So we're going to have y equals 3 times the cube root of negative 11 plus 3 plus 1. Y equals 3 times the cube root of negative 8, which is negative 2 plus 1. Y equals negative 6 plus 1, which is negative 5. We are now going to plot these points and get a more precise plotting. Okay, so we have, first point is going to be 5, 7, 2, 4, 5, 2, 4, 6, 7. And our final point is going to be x equals negative 11, y equals negative 5. So we have 3, 6, 9, 11, 2, 4, 5. Okay. Here is our final graph connecting these points. Our inflection point is going to be the middle of the vertical segment. Let's try to do that. Here's our vertical segment, and then it curves this way. Okay, checking that out on the graphic calculator, we see that this blue graph here, you can see it, the radio button is indicating the blue graph corresponds to this equation, 3 times the cube root of x plus 3. Here it is, the blue, the exact graph that we just saw. Let's now endeavor to graph this function. Before we do that, we take a quick look at it and we see that the signs are different, plus out in front, minus inside the radical. So we know this graph is going to move down. We see that the a value, the absolute value thereof, is 1, so we know the vertical segment is going to be perfect. But what we don't know is the inflection point, and the reason is this coordinate, this coefficient, in front of the x is not positive 1, it is indeed negative 1. So the first thing we want to do is manipulate the original function in order to get that coefficient to positive 1. So another example when I forgot to put 3 there. So we're going to pull out a negative 1. This becomes x minus 2. And I always double check my work when I do something like this. Negative 1 times x is negative x. Negative 1 times negative 2 is indeed positive 2. Folks, this is a product. When you have a product within a radical, you can make it 2 separate radicals as long as you keep that root the same. So we're now going to have the cube root of negative 1 times the cube root of x minus 2, and let's not forget our plus 3. This is going to become negative 1, cube root of x minus 2 plus 3. We are now ready to extract the inflection point. We're going to put a circle around the minus 2, and as we pull that out, we're going to change that to plus 2 for the x coordinate, and we're going to keep the y coordinate or the k coordinate exactly as is. So folks, positive 2, positive 3 is our inflection point. So let's go ahead and graph that and proceed. Okay. We have positive 2, positive 3 right there. We are now going to go look at the x coordinate of the inflection point. We're going to go 1 to the right, which is going to be 3. And we're going to go 1 to the left, which is 1. We're going to determine f of 3 and f of 1 in order to get the y coordinate. All right. If we put 3 into this equation, we have the cube root of negative 3 plus 2 plus 3. That's going to be the cube root of negative 1 plus 3. Negative 1 plus 3 equals 2. So our y value is going to equal 2. And when we do f of 1, we're going to have the cube root of negative 1 plus 2 plus 3. This is going to be the cube root of 1 plus 3. 1 plus 3 equals 4. Okay, folks, we have several points now. Let's go ahead and graph them. First point is going to be 3, 2. 3, 2. And the next one's going to be 1, 4 right here. Okay? And this already makes sense because we're moving down from our inflection point as predicted by the fact that these signs are different. Okay, the next thing we're going to do is we're going to set what's under the radical equal to 8 and solve for x. So we're going to get negative x equals positive 6, x equals negative 6. So we are going to go ahead and do f of negative 6. Negative 6 plugged into this equation would give you the cube root of positive 8 plus 3. The cube root of positive 8 is positive 2 plus 3 is 5. Okay. Next, folks, we're going to set x plus 2 equal to negative 8. Again, we're setting the radical equal to perfect cubes. Okay. We're going to have negative x equals negative 8 minus 2, which is negative 10. X equals positive 10. We're now going to do f of positive 10. If we put positive 10 in here, we're going to get the cube root of negative 8 plus 3. The cube root of negative 8 is negative 2, plus 3 would be positive 1. Okay, let's go ahead and graph these points. We're going to have 10, 1. And we're going to have negative 6, 5. Okay. We now have enough points to accurately graph this. We could see that the vertical distance on this graph is perfect, as indicated by the absolute value of A being 1. So let's go ahead and draw that. Here's our, it's not a very good vertical segment, but you get the idea. And if we go to our graphing calculator Desmos, here's our graph, negative x plus 2, the cube root thereof plus 3, and you could see that we got the same graph right here.